Hello everybody. Hope you are in good health. In today's lecture we will discuss about the enthalpy of formation and enthalpy of combustion. The content will be covered from the textbook Thermodynamics, An Engineering Approach, 5th edition, by Eunice A. Sengel, and Michael A. Bowles. In this lecture we will cover the following contents: enthalpy of formation, enthalpy of combustion, heating value, higher heating value, and lower heating value. The molecules of a system possess energy in various forms such as sensible and latent energy, associated with a change of state. Chemical energy, associated with the molecular structure. And nuclear energy, associated with the atomic structure, as illustrated in figure. At this level we do not intend to deal with nuclear energy. We also ignored chemical energy until now, since the systems considered in previous chapters involved no changes in their chemical structure, and thus no changes in chemical energy. Consequently, all we needed to deal with were the sensible and latent energies. During a chemical reaction, some chemical bonds that bind the atoms into molecules are broken, and new ones are formed. The chemical energy associated with these bonds, in general, is different for the reactants and the products. Therefore, a process that involves chemical reactions involves changes in chemical energies, which must be accounted for in an energy balance. When the existing chemical bonds are destroyed and new ones are formed during a combustion process, usually a large amount of sensible energy is absorbed or released. Assuming the atoms of each reactant remain intact, no nuclear reactions, and disregarding any changes in kinetic and potential energies. The energy change of a system during a chemical reaction is due to a change in state and a change in chemical composition. That is, energy change of a system during a chemical reaction is due to a change in state and a change in chemical composition. Therefore, when the products formed during a chemical reaction exit the reaction chamber at the inlet state of the reactants, we have change in state is zero, and the energy change of the system in this case is due to the changes in its chemical composition only. In thermodynamics we are concerned with the changes in the energy of a system during a process, and not the energy values at the particular states. Therefore, we can choose any state as the reference state and assign a value of 0 to the internal energy or enthalpy of a substance at that state. When a process involves no changes in chemical composition, the reference state chosen has no effect on the results. When the process involves chemical reactions, however, the composition of the system at the end of a process is no longer the same as that at the beginning of the process. In this case it becomes necessary to have a common reference state for all substances. When the process involves chemical reactions, however, the composition of the system at the end of a process is no longer the same as that at the beginning of the process. In this case it becomes necessary to have a common reference state for all substances. The chosen reference state is 25 degrees Celsius, 77 degrees Fahrenheit, and 1 atm, which is known as the standard reference state. Property values at the standard reference state are indicated by a superscript, degree, such as H degree and U degree. When analyzing reacting systems, we must use property values relative to the standard reference state. However, it is not necessary to prepare a new set of property tables for this purpose. We can use the existing tables by subtracting the property values at the standard reference state from the values at the specified state. The ideal gas enthalpy of nitrogen at 500 K relative to the standard reference state. We can use the existing tables by subtracting the property values at the standard reference state from the values at the specified state. For example, now we will see in another example for better understanding. Consider the formation of CO2 from its elements, carbon and oxygen, during a steady flow combustion process. Both the carbon and the oxygen enter the combustion chamber at 25 degrees Celsius and 1 atm. The CO2 formed during this process also leaves the combustion chamber at 25 degrees Celsius and 1 atm. The combustion of carbon is an exothermic reaction, a reaction during which chemical energy is released in the form of heat. The process described in previous slide involves no work interactions. Therefore, from the steady flow energy balance relation, the heat transfer during this process must be equal to the difference between the enthalpy of the products and the enthalpy of the reactants. That is, since both the reactants and the products are at the same state, the enthalpy change during this process is solely due to the changes in the chemical composition of the system. This enthalpy change is different for different reactions, and it is very desirable to have a property to represent the changes in chemical energy during a reaction. Enthalpy change is different for different reactions, and it is very desirable to have a property to represent the changes in chemical energy during a reaction. This property is the enthalpy of reaction, which is defined as the difference between the enthalpy of the products at a specified state and the enthalpy of the reactants at the same state for a complete reaction. For combustion processes, the enthalpy of reaction is usually referred to as the enthalpy of combustion, which represents the amount of heat released during a steady flow combustion process when 1 kmol, or 1 kg, of fuel is burned completely at a specified temperature and pressure. To establish a starting point, we assign the enthalpy of formation of all stable elements, such as O2, N2, H2, and C, a value of 0 at the standard reference state of 25 degrees Celsius and 1 atm. Now reconsider the formation of carbon dioxide, a compound, from its elements carbon and oxygen at 25 degrees Celsius and 1 atm during a steady flow process. That is minus 393,520 kJ per kmol. The negative sign is due to the fact that the enthalpy of 1 kmol of carbon dioxide at 25 degrees Celsius and 1 atm is 393,520 kJ less than the enthalpy of 1 kmol of carbon and 1 kmol of oxygen at the same state. In other words, 393,520 kJ of chemical energy is released, leaving the system as heat, when carbon and oxygen combine to form 1 kmol of carbon dioxide. Therefore, a negative enthalpy of formation for a compound indicates that heat is released during the formation of that compound from its stable elements. A positive value indicates heat is absorbed. You will notice that two enthalpy of formation values are given for H2O in Table A26, one for liquid water and the other for water vapor. This is because both phases of H2O are encountered at 25 degrees Celsius, and the effect of pressure on the enthalpy of formation is small. Note that under equilibrium conditions, water exists only as a liquid at 25 degrees Celsius and 1 atm. The difference between the two enthalpies of formation is equal to the HFG of water at 25 degrees Celsius, which is 2441.7 kJ per kg or 44,000 kJ per kilomole. Another term commonly used in conjunction with the combustion of fuels is the heating value of the fuel, which is defined as the amount of heat released when a fuel is burned completely in a steady flow process and the products are returned to the state of the reactants. In other words, the heating value of a fuel is equal to the absolute value of the enthalpy of combustion of the fuel. The heating value depends on the phase of the H2O in the products. The heating value is called the higher heating value, HHV, when the H2O in the products is in the liquid form. And it is called the lower heating value, LHV, when the H2O in the products is in the vapor form. The two heating values are related by the equation given below, where m is the mass of H2O in the products per unit mass of fuel and HFG is the enthalpy of vaporization of water at the specified temperature. Higher and lower heating values of common fuels are given in Table A27. Now we will solve a problem, evaluation of the enthalpy of combustion. Statement is: determine the enthalpy of combustion of liquid octane, C8H18, at 25 degrees Celsius and 1 atm, using enthalpy of formation data from Table A26. Assume the water in the products is in the liquid form. The enthalpy of formation at 25 degrees Celsius and 1 atm is extracted from Table A26. The stoichiometric equation for this reaction is: Both the reactants and the products are at the standard reference state of 25 degrees Celsius and 1 atm. Also, nitrogen and oxygen are stable elements, and thus their enthalpy of formation is 0. Then the enthalpy of combustion of C8H18 becomes, as we already discussed, that enthalpy of combustion must be equal to the difference between the enthalpy of the products and the enthalpy of the reactants. In this equation HF is the enthalpy of formation and N symbolized the number of moles. We can calculate the enthalpy of combustion by substituting the equation. Calculated value is practically identical to the listed value of 47,890 kJ per kilomole in table A27. Since the water in the products is assumed to be in the liquid phase, this enthalpy of combustion value corresponds to the higher heating value of liquid C8H18. Thank you.